we created something that we called the loan month model. And a loan month model is basically something that instead of modeling a single terminal state of the loan, like do you repay the loan at all, we built an architecture that separately predicts default and prepayment in every individual month of a loan's life. That basically meant that instead of having sort of a single prediction we were now making for a 5-year loan 120 distinct predictions. And that meant that we could suddenly start applying all the modern machine learning algorithms to this problem, because each problem was sort of a distinct and completely discrete problem that would be deterministic in what its sort of resolution state was. Now, you might think, oh, okay, that's cute, but does that really matter? And the answer is yes, it matters massively. So I'll just give you a specific example to illustrate the point. So let's take two borrowers. Borrower A has a lifetime chance of defaulting on their loan of 12.65. Another borrower, borrower B, exactly the same lifetime default probability. But what you see in this graph are two curves. The blue curve representing borrower A shows you their default probability in each month of a 60-month loan, and the same for borrower B. And you can see that despite ending up at the same place, this is a cumulative curve, the trajectories they take to get there are radically different. And specifically, they're different in the way that borrower A is a fair bit more likely to default in the first year of the loan's life. Borrower B becomes a fair bit more likely to default in the second half of the loan's life. And this matters a lot, not surprisingly. Now, if you use a traditional approach and you assume a fixed curve, then you're stuck sort of taking something in between, and that's what would happen. You might have an average timing curve as represented by this gray line for your population, and you just assume that's the ratio. That's when I expect that defaults actually happen without having a model that has the ability to sort of make these individualized predictions. But you would get the underwriting terribly wrong, because the actuarially correct APRs for these borrowers turn out to be really, really different, despite having the same probability of paying back the loan. Borrower A's optimal APR, meaning like the actuarially correct thing that solves for your target return with precision, is 16.7%. Borrower B is at 13.09%. And that difference, 361 basis points, is a very large number. And if you're taking a traditional approach here, you're essentially forced to be hundreds of basis points wrong in one direction or the other. And with the loan month model framework, we were able to solve that problem.